Halloween, we have quite a treat to have with us Dr. Marina Kounkel. Dr. Kounkel, fun fact, she grew up in Kazakhstan and moved to the US when she was in high school, 9th grade, right? Quite a cultural shock, but she did quite well. She ended up going at University of Toledo, then did her PhD at University of Michigan. Well, where she made herself quite an expert in young stars, especially in all the stars in Orion and all that, and went on to do 2 postdocs, one at Western Washington University with Kevin Covey, and one at Vanderbilt University with Kevin Stasson, and has made a number of really important papers on the motions and locations of young stars near the sun, not so young, all the way to 1 billion year old. So she knows where all the young stars are within a few kiloparsec of the sun, basically. You just ask her. And now she's got a position as an assistant professor at University of North Florida, so she's almost a neighbor. And she's doing absolutely amazing work. So, Marina.
Thank you all for having me here today. When we look out in the sky, we see thousands and thousands of stars. And all of them are part of our home galaxy, the Milky Way. And if we are actually move far enough away from city lights, we are able to see this diffuse light that corresponds to the disk of our galaxy. But when we look out on the sky, what we see is a flat, almost static representation of the world around us. And one might wonder, well, how precisely did we come to be where we are? Our galaxy is a very dynamical place. It keeps twisting and turning. The structure within it keeps coming and going. But throughout all of the time that our galaxy has existed, it was forming stars. And even so the galaxy may reshape itself many times over, the stars remember. The stars remember where they have formed, what were the initial conditions of the gas from which they have formed, what were conditions that have led to their formation. So in principle, if we were to know everything about these stars, if we were to know where they are currently, if we know how fast they are moving and in which direction, and if we know how old these stars are, in principle, we could turn back the clock and figure out, well, where do they come from? And nowadays, we have pretty good understanding of stellar positions. We have pretty good understanding of stellar velocities, but the ages are a tricky bit. Ages of the stars have always been non-trivial to measure, at least for the most of them. There are some exceptions. The best way for us to be able to estimate stellar ages is to observe them in clusters, such as, for example, these. Here we have Pleiades, here we have Orion Nebula, global clusters, they all look alike. Because when stars are in a cluster, all of them have formed at the same time, and you have stars of different masses. Some of them are high mass, some of them are low mass. And through comparing their brightnesses to theoretical models, we can determine the age of a cluster as a whole. So we can use these clusters as stellar laboratories for understanding stellar and galactic evolution. And nowadays, it's a perfect time to study clusters because we live in the era of Gaia. Now, this is a combined department. I don't know if all of you are familiar with Gaia, but what Gaia is a telescope that very accurately measured positions and the velocities of stars. And because all the stars in the cluster are kind of located in the same space and they're moving with the same velocity, it becomes very, very easy to find them with Gaia. Gaia has influenced almost every single aspect of galactic understanding, galactic astronomy, but where it made the most impact is in the study of these structures. And just kind of to demonstrate how significant it was, here we're looking at a map of our galaxy face down. The sun is at the center. The galactic center is to the right of this image. And in red are all of the different clusters that we have known about before Gaia. And all of these black dots are the clusters that have been found in just one of about a dozen of different studies where they have found more and more of these structures. Clusters are everywhere. They are ubiquitous. They are unavoidable. People are starting to break their limbs tripping over them as they're looking through the data. And in fact, people who actually do search for these structures kind of probably have thrown their hands up in the air and yelled out to the sky, because we no longer know what clusters are, because there's such a vast variety of them. So there have been a lot new populations that have been found out, from which we are able to estimate ages. And indeed, we're no longer are concerned with just clusters. Again, the word cluster started to lose its meaning. We can find a lot of various moving groups. That is to say, the groups of stars that have all formed at the same time, but may not necessarily be gravitationally bound. And here, in comparison, in yellow are previously known open clusters within a volume of space of 1 kiloparsec. And in blue are all of the new clustered stars that have been found in the same volume of space, and just a completely different sense of scale. So there are more than 8,000 such populations within 3 kiloparsecs, consisting of more than 1 million stars. And we can use these moving groups just as well as we can use clusters for the age determination. Here we have the HR diagram, where you can see that the youngest populations in red still having a very sizable pre-main sequence on the low mass end. Eventually, as they get older, they fall down onto the main sequence. And then after about 100 million years, the high mass stars begin to die off in increasingly larger numbers. So you do end up with a fairly cleanly defined turnoff. So you can use these populations to have a very good sample of stars with known ages, largest that we ever had, probably larger by an order of magnitude compared to where we were about a decade ago. But unfortunately, that's not enough. There are billions of stars out there, and just 1 million is like a drop in the bucket. It's excellent that we have it, but there are many more stars out there. And these populations tend not to be gravitationally bound. And after a star orbited, after a population orbited around the galaxy just once, well, most of the populations will be completely dissolved. And even the ones that are still out to this, around to this day, they will be missing a large extended structure that would have once existed around them. So they're just a shadow of the former self. And if we are to, here we see that it's easiest for us to recover all these populations at the youngest ages. But if we were to assume that the star formation history of our galaxy is such that it produced the same number of stars in a given period of time, this would be a lot of stars to miss. So we need to search for other techniques to be able to estimate their ages if we want to be able to point at any star in the sky and be able to estimate its age. And here you can see that even the youngest clusters aren't really free from this simulation, but here in a second you will see that there are 2 stars that are kind of a, give it a second. Yeah, here you see how the 2 stars kind of got ejected from the cluster. So even at the youngest ages, you have some stars that are very eager to leave their nest, and some do it much more violently than others. Here are some of the actual data. This is Orion Nebula, which is one of the youngest, very massive clusters that we have in the solar neighborhood. And there have been several dozens of runaways that have been identified around this cluster, where they are just moving on these radial trajectories with very, very fast speeds. We would not be able to recover them using the traditional clustering techniques that we would be able to, that we currently are using to identify these populations. So we need something else. If we restrict ourselves to just low mass stars younger than around 60 million years, well, these stars are still pre-main sequence. And we could fairly carefully trace out this corner of the parameter space, very carefully avoiding the main sequence, the binary sequence, all those awful red giants that tend to scatter into the parameter space of where pre-main sequence stars live. But through doing all of that, we can get a fairly clean sample of all of the young stars in the solar neighborhood. And if we do a slightly less careful job, we would be able to push our age limit a bit further, but we would end up with slightly more contamination as a result, because as you get closer to the main sequence, it just becomes really hard to separate them out. But here we are able to estimate ages of each and every one individual stars. because just looking at the position of these stars above the main sequence, that would correspond directly to their age. And through making the selection, we can see where all the young stars are in the sky. So here, this is a map of our young solar neighborhood. Here's the galactic plane. Here are all the different populations. And here is the exact same range of population that we can recover through clustering. You can see there's a very different sense of structure that we are able to see when we are much more complete in our selection. And we can take all of these stars and we can separate them out into different layers based on their age. So here we're just looking at the stars that are younger than 2 million years. And we are able to recover all the various star forming regions that we have around us: Orion, Ophiuchus, Taurus, Perseus. So I don't think there's too many people who are doing star formation in this department. But believe me when I say that 95% of everything that we know about star formation came from these regions. So prior to Gaia, we haven't really looked much beyond them. 2 to 5 billion years, we're starting to bulk up the same regions. We're getting a much bigger structure around Orion. We're having more stuff around Ophiuchus. We're getting more distant populations such as NGC 2264 and Cygnus. And is it possible to remove the, yeah, that doesn't matter. Here is 5 to 10 million years. Again, starting to fill up more and more stuff around here. Vela, I would like to highlight this population in particular because very few analysis of it have been done before Gaia came online, but since then it has become quite a favorite region for many. And again, it doesn't want to work. Sorry about that. 10 to 16 million years, 16 to 25 million years. And finally, at the ages of greater than 25 million years. This is basically terra incognita, because even so we have had various techniques to identify young stars in the past, we would not have been able to be sensitive towards the ages this old. And similarly, the people who study open clusters wouldn't have really paid attention to these stars because they're just too distributed. They're not compacted in a cluster. So there's a lot of potential in being able to analyze the star forming history of the solar neighborhood. And in fact, if we were to take all of these stars and look at our galaxy top down, here's galactic, their sun is going to be right over here. Galactic center is to the right. And you might notice right over here, there is this weird ring that is traced by these young stars. That seems unusual, almost improbable. Why would the sun be at the center of something? Except we know that the sun is located, completely coincidentally, at the center of a local bubble. Local bubble is a region where we don't have much gas, where we don't have any dust, where we see some diffuse interstellar bands that formed as a result from some old X-ray emission. So the shape of the local bubble matches the dimensions of the string pretty well. So chances are many of the young stars that we have around us actually do have some common history, that there was some event that has produced this local bubble and that could have led to their formation. So this is all well and good. We can identify all the pre-main sequence stars and we can do a lot with them. But what if we wanted to go beyond 60 million years? That no longer works because as you get towards older and older ages, you get closer and closer to the main sequence, you just get swarmed with contamination. So we need to search for other techniques. Well, young stars tend to be very strongly magnetically active. That magnetic activity tends to produce spots on the surface of these stars. And some of these spots can be extremely, extremely massive, containing, encompassing well over half of the surface of the star in comparison to our sun, which tends to have fairly wimpy spots. But as these spots, as they start to rotate around this axis, the spots drift in and out of the field of view. And so we are able to see the star change in its brightness. It will become slightly brighter, then it becomes slightly fainter. And it will occur on the timescales of a rotational period of a star. And the larger the spot, the greater the variability is going to be. The small spots are hardly going to perturb the brightness, but very large spots would have a very large amplitude, extending several percent of the total brightness of a star. And so we can estimate the sizes of these spots just by looking at the amplitude of variability. It's not a perfect tracer, but it gets us most of the way there. So we can take all of the stars for which we currently know ages in these moving groups, and we can see how the spots in them evolve. And so here we have age versus temperature of a star. Here we have all of the youngest stars, and they're color-coded by approximate spot size. And these pre-main sequence stars tend to have very, very, very large spots on their surface. And the stars that remain fully convective throughout their lives, the low-mass stars, right over here, they retain a high degree of spot coverage on their surface. But the stars that are not going to be fully convective, stars like the sun, well, eventually they will start developing a radiative zone within them, and after they reach the main sequence, well, after that, the spots are barely a fraction of what they once were. So our sun has a temperature of around 6,000 Kelvin, and it's pretty old, so it's right over here, but originally it would have started its life somewhere over here. So this is something that we have known about for a while. We have built models about how stars should behave, but it's still very nice to be able to see it empirically with the data directly. And spots are a transient phenomenon. They do not stay statically on the surface of the star. They tend to move around, they break up, they reform. Sometimes you might have several spots, sometimes you don't have any on the surface. So for some stars, if you were to observe their light curves over a very long period of time, you can see how the morphology of this light curve changes, because spots change themselves. But throughout all this time, throughout the period of several years, the rotational period remains the same. So you still have the same star that is still rotating at the exact same rate. And over the course of our human lifetimes, we should not expect that to change significantly. But if we were to consider the lifetimes of stars, then we would be able to see significant evolution in the rotation rate. Because the stars, when they're just born, they have a very high degree of angular momentum. They tend to spin around very fast. But the same magnetic fields that are responsible for the production of the star spots are also slowing down the rotation of the star. So they're dragging the star down. And as a consequence, you have very young clusters having fairly short rotational periods. Stars within them fairly short rotational periods. And as you get towards older and older stars, the rotation periods is significantly slower. So in principle, if you know the temperature of a star and you can measure its rotation rate, you might be able to infer its age through the technique known as gyrochronology. But this diagram is pretty sparsely populated, as you might see. The best, yes?
Do you have a size comparison between young stars versus older stars?
Size comparison, you mean the physical radii?
The physical radii.
We do. So the stars that are on the main sequence, they don't change the radii all that much. We have models of how the radii do evolve. There are some stars for which we are able to measure radii more precisely, but it's a matter of scale. So I don't think we have as precise of a radii as we're hoping to need to do this type of analysis for the bulk of the stars. And it really would only work for the stars that are very young or very old, not the stars that are on the main sequence. So these gyrochronology is able to discriminate between ages of the stars that are still on the main sequence, which is what makes it nice. But yeah, this diagram is very sparsely populated because until recently, the best source of light curves we had came from the Kepler mission. Kepler stared at a given region of her sky for many, many, many months. And so it observed the same star over and over and over again with very high degree of precision. But Kepler had a very limited field of view. So within that field of view, you had only a handful of clusters that can be used to calibrate gyrochronology. Nowadays, so that has changed slightly. We do have a better mission called TESS. TESS has a much larger coverage. So that to the degree where if you pick almost any star up to a certain brightness, you would be able to generate its light curve from the data from TESS. Now, TESS is not quite as well calibrated as Kepler, unfortunately. So it is some of these light curves may not necessarily look quite as nice as they would with Kepler. And also, TESS is staring at every single sector of the sky for a much shorter period of time, of only about 1 month. So you can't really push it to the rotational periods as long as you would with Kepler. But still, there's a lot of stars for which we do know ages. So let's see how the rotational periods look like. And here we have a temperature of a star relative to the period that we are able to recover from the light curves of these stars. And right over here at temperature of around 6,700 Kelvin, there's a very interesting gap. So this gap kind of separates out the stars that have convective envelopes. These stars with convective envelopes are able to form spots on their surface, and the stars with radiative envelopes, which cannot. So these stars on this side of the diagram, their variability comes from rotation. These variables right over here, they tend to be pulsating variables. Those to say they shrink back and forth, so that's why they change their brightness. It still happens with a certain period, so they did end up in here. I won't spend too much time among these pulsating variables. There are many different types of them. There is this instability strip, which these stars intersect. So we have delta Scuti stars, gamma Dor, slowly pulsating B-type variables. I'll just mention that there are a few interesting age trends that we see among these pulsating variables as well. For example, delta Scutis. They tend to have periods of less than a few hours, but if you were to take all the delta Scuti variables, they will have a complete coverage of these periods from up to a couple of hours. Here we see more of a bimodal distribution, such that all of the main sequence stars tend to have much shorter periods. All of the subgiants tend to have longer periods. And this is because this is an age-limited sample. So all the stars that will fall in between just haven't evolved to that point yet. So that's quite nice. But on this side of the diagram, we do have all of the rotating variables. And rotating variables come in two different flavors. You have slow rotators, and we have fast rotators. And in slow rotation in particular, you see this very, very nice gradients that very young stars tend to have very short periods of rotation, and older stars tend to slow down the rotation significantly. And the reason why we only go up to the periods of 10 days is, once again, because TESS has such a short baseline in time. So we can't push it longer than that. But looking at it in this parameter space, it's nice, but it's not particularly usable. For example, you can't really determine ages for the stars cooler than around 4,000 Kelvin, because you can see it kind of turns over like this, like a horseshoe. And the stars of different ages get stacked on top of one another. So you have both very young stars and much older stars in there as well. But thankfully, there is a different type of law that we can make that would make it much clearer what's actually happening here. Because if we can estimate the masses of the stars, and if we can estimate the radii, and since we know the periods, we can look for angular momentum. And as you can see, that everything kind of gotten straightened out. Young stars begin their lives with very high degree of angular momentum. And as they age, they lose angular momentum over time. And we no longer have this weird turnoff because young stars, even though they don't really change their periods all that much, they do shrink down as they get to the main sequence. So they're still losing angular momentum over time, even if you wouldn't necessarily notice it in the periods alone. So in this parameter space, it's possible to fit a pretty straightforward polynomial that would unambiguously relate the rotational period and angular momentum to the age of a star. We unfortunately not quite at a point where we have rotational periods of all the stars across the entire sky. That might be coming in another couple of years as people get more hands-on with TESS data. But it will be coming, and eventually it might be possible to use this technique to increase the number of stars for which we do have ages by an order of magnitude. Right now we can apply it to the stars that have been observed by Kepler. And again, there's only a handful of clusters in the Kepler fields. But for example, Pleiades, NGC 6811, Upper SCO, and Praesepe, we are able to recover the ages of these clusters to be what we expect them to be from all the other techniques. And everything else is seems to be more or less reasonable. Unfortunately, it's a bit more complicated than that. So there's always going to be caveats. And I've mentioned there are two types of rotators. There's slow rotators that do follow this very nice gyrochronology relationships, and they're fast rotators. And fast rotators, they also lose angular momentum over time, so they also spin down, but they begin their lives with much faster rotational velocities than the slow rotators do. Why might this be the case? Why are they spinning so fast in comparison to everything else? Well, we can try to figure out what they are. If we were to pick just a small age slice, just so we wouldn't have much confusion about what rotational periods these stars should have, we can plot an HR diagram. And so here we have a cluster sequence, and stars on that cluster sequence tend to rotate with a particular period. But here we have the binary sequence, where we have the stars that basically the system of two stars that are unresolved from our observations. They appear to be brighter than the main sequence stars. And you can see that they tend to have rotational periods much faster than you would have in single main sequence stars. And here's another way of looking at it. So here we have in blue the stars on the main sequence, preferentially slow rotators. And the stars on the binary sequence are overwhelmingly tend to be rapid rotators. So it's not precisely one-to-one, but it does imply very strongly that there's something about multiplicity in particular that is responsible for rapid rotation. Now, why could this be the case? Well, one obvious explanation might be if you have two stars very close to one another, then eventually their orbital and rotational rate tends to sync up. Except that can't be an explanation, because this is a distribution of all the orbital periods that binaries tend to have. The most likely orbital period between a pair of stars is on the order of the typical separation is on the order of 30 to 40 AU, which corresponds to periods of, I think, a few hundred years. And the stars that would be tidally locked and their rotational and orbital rate would be synced would be right over here. Probably not even in the first bin. So there's only a handful of those stars that could exist. They couldn't account for this vast wealth of rapid rotators that we actually do see. So there's something else about multiplicity that should account for it. And in fact, we see rapid rotators to be less likely around spectroscopic binaries, where you have periods of only a few hundreds to a few thousands of days. So it's unlikely to be at very short separations. And these binaries are unresolved. Therefore, it's unlikely to be at very long separations either. So you need to be kind of in a sweet spot of separations of a few to few tenths of AU. So in order to figure out why this might happen, we should look at the earliest stages of star formation. So we can take a look at stars in Orion complex. And here's a picture of Orion. I really like looking at it in these very long exposure images, because if you know how to look at it, it just shows the wealth of structure of young stars that is actually present in this constellation. And so you have Orion A molecular cloud, Orion B molecular cloud, and the rest of it is also filled with young stars with ages of up to 10 million years. You have a great diversity of environments in there. You have great diversity in ages of young stars and what types of stars they are. Many of these stars still have protoplanetary disks. Many of them have long since lost them. So this is a particularly unique region for which we have a lot of data about these stars to be able to determine their properties. And if we're to take a look at all of the stars for which in Orion for which we have been able to measure rotational periods and separate them out based on whether they still have protoplanetary disks or not, what we see is that the stars with protoplanetary disks in red, you don't really see many of them with rotational periods less than 2 days. Because these stars, since they still have disks, the inner rim of the disk is rotating with particular speed, and the star tends to be locked to that disk. So the star would be forced to rotate with the same speed as the inner rim of the disk. That's why we don't have many rapid rotators that still have disks. On the other hand, as soon as stars lose their protoplanetary disks, they are able to speed up. But in Orion, we also have, again, we have a lot of data, including the data on the ages of the individual stars. So we can see how this changes at different age bands. So we can separate out the sample into stars that are extremely young, less than 1 million years old, 1 to 3 million years, and 3 and older. And again, in blue are the stars without disks, in red are the stars with disks, and in black are all of the sources. And you can see that throughout all ages, the overall fraction of rapid rotators, that is to say, all the stars with periods less than 2 days, remains flat. So whatever rapid rotators you have early on, you will have later on as well. But the stars that are most likely to lose their disks first would be rapid rotators. And if rapid rotators are binaries, well, binaries interact with disk in different ways than single stars. Binary stars are much more likely to destroy their disks early on just through orbital dynamics. So very early on, binaries would lose their disks, and binaries are the ones that to be most likely to be rapid rotators. Eventually, all stars will lose their disks, both single and multiple. So as the time goes on, this will trend towards the median. But the stars with disks, I mean, initially, you have very few of them being rapid rotators. And then most of the stars will lose their disk. By the end of it, you have only a handful of them still left over. But if you somehow manage to preserve the disk for a very long period of time, the disk will not be able to suppress rotation indefinitely. So eventually, the star would accrete excess angular momentum and would still speed up, even if you haven't completely disrupted the disk. So why is this happening? There are some models. I'm not sure how reliable they are, but there are some models that suggest that binary stars are less effective at getting rid of angular momentum in comparison to single stars. That is to say, binary stars don't drive the outflows quite as well as single stars do. And since you need these outflows to get rid of the angular momentum, they just end up preserving much more of it in the system in comparison to single stars. So originally, they might start with the same degree of angular momentum, but single stars would lose it much more rapidly in the early stages of star formation. So you would end up with this bimodal population of rapid rotators and slow rotators, being single and binary stars. So we've been looking at Orion, and Orion is nice because we know a lot about these stars. But unfortunately, well, here in these older clusters, we can see the cluster sequence defined very, very well. We also have the binary sequence defined very, very well. That's how we can infer that these stars are binaries. In Orion, it's a bit more difficult to do because Orion, it's still so young, and all the stars wouldn't evolve so rapidly that you end up smearing the cluster sequence. So that even so you do still have binary stars in here, you also have an intrinsic age spread that completely masks it. So it's kind of hard to piece out. So how might we be able to confirm that even at these youngest ages, rapid rotators are binaries? Well, what we can try to do is try to measure inclination of stars. What inclination is a completely arbitrary number. Stars can have any inclination relative to us that is possible. It's a completely random property. But by calculating inclination, we can learn a lot about the biases that we have behind our observations. So the way that we would measure the inclination is we can try to estimate stellar radii, which is kind of going back to the question that you have had before. So to estimate stellar radius, if we know the rotational period of the star, and if we know its rotational velocity, we can perform a simple estimation to get the radius, except we don't measure rotational velocity, we tend to measure v sine I. So by that, we will have r sine I as the thing that we are able to estimate using this method. And we can also estimate the radius of the star if we know how bright it is, and if we know how hot it is, and if we know how far away it is, we can simply rearrange it to be able to estimate the radius. And combining these things, we are able to infer the inclination, which would depend on the temperature, the period, rotational velocity, distance, and the brightness of the star. Again, this is a completely meaningless value for most applications in astronomy beyond figuring out what biases you have. To kind of show what I mean by that is, let's compare the stars in Orion that tend to have very strong variability versus the stars that tend to have very weak variability. And what we see is that the stars with very strong degree of variability tend to be almost completely edge-on. On the other hand, the weakly variable stars tend to have a much larger spread in their inclinations, but most preferentially tend to be not quite as edge-on as the other ones. And if you think about it, if you have two identical stars with two identical spots, which in Orion you still have very, very large spots. So let's presume that we have identical spots on both of these stars. But one of them is faced towards you edge-on, and as it's rotating around its axis, the spot will be able to fully rotate in and out. It will cause a very high degree of variability. On the other hand, the star that is more inclined, the spot would not be able to rotate quite as fully. So the variability is going to be suppressed because there's going to be a portion of the spot that will either never rotate in or out of the field of view. So that's why we have very strongly variable stars to be preferentially edge-on. Orion, being so young, and since it has such massive spots, we tend to be able to see them no matter what inclination you have. In older stars, if you still see them being variable because the spots do shrink down over time, the stars in which you are still able to detect variability within our completeness tend to be preferentially edge-on. So if you have a really, really old star, you wouldn't really expect any orientation other than almost completely edge-on. And in fact, if you do try to do it with some variables in TESS, that's what you end up getting. But so how does this help us with the rapid rotators? Well, if we were to go back to this equation, this implicitly assumes that you have a single star because you cannot measure radius with two stars. But if you do have two stars, the overall flux of the system is going to be brighter than when you do have a single star. And so if you overestimate the flux, you would underestimate the inclination. And in Orion, that's precisely what we see. If we were to separate out the stars into the slow rotators and the fast rotators, we see that the slow rotators tend to have the distribution of eccentricity of inclination that we do expect, but inclinations that we would infer from rapid rotators are systematically smaller than the inclinations of the slow rotators. This once again suggests that these rapid rotators are binary stars. And again, in the older stars, because you do expect almost all of them to be edge-on, if you do see a populations of stars that have inclinations other than edge-on, you should be very careful in applying gyrochronology towards them. So this may allow us in the future to separate out the slow rotators and the fast rotators as we are able to get better and better stellar parameters for all of these stars. So to bring it to a close, in the last decade or so, we have progressed significantly in being able to estimate ages of stars with discovery of all of these new moving groups and through developing more and more techniques in order to be able to estimate their ages. And in the next decade, we are hoping to expand the census by yet another order of magnitude as we are able to actually employ some of these other techniques that are based on the variable stars, which are now accessible to us through the advancements of various large surveys. Thank you so much.
Then do you have time for questions?
You had a slide that was like titled Rapid Rotators Occupy the Binary Sequence, the very first time you showed it.
Uh-huh.
I know yeah, right here. You said something to explain it, but could you explain why you see a bimodal distribution in the binary stars?
You mean here?
Yeah.
Yeah. So not all of the stars not all of the binary stars are going to be rapid rotators. If you have very close binaries, those tend to not be rapid rotators. If you have stars that are very, very far apart, with separations of over 100 AU, those are not likely to be rapid rotators. In fact, there are a couple of cases where we actually do have resolved observations of, for example, in Taurus, where we see stars having, where we know that the stars where we know the stars are binaries, basically. And we can tell that if the stars have separations of greater than 3, but less than around 40 or 50 AU, those tend to be rapid rotators. So not all of the binaries would end up there. Also, there's still a lot that we don't know about the parameter space. It could be just different masses ratios or some other factors. Mm-hmm.
On the next slide, there's the plot where I think it's the TESS data. You showed that horseshoe, right? So for those cool rapidly rotating stars, are those all? Are the binaries included in this, or are these just the young stars?
Yeah, so this has everything for which we have ages. So binaries would also be here. For the M dwarfs, it's kind of more difficult because, as you can see, the slow rotators and the fast rotators are also kind of starting to coincide. Whether you have the similar physics at work or not, M dwarfs are mysterious.
Why you get the horseshoe shape?
Yeah. So it's just basically kind of how mass and radius in a star scale. Okay. So if you look at just as angular momentum, you can see that it's much smoother. But just because of how mass and radius would kind of trade up, it ends up counterbalancing. Mm-hmm.
One of your early color magnitude plots showed a population of white dwarfs. Potentially means these are some youngish white dwarfs, which can be helpful for establishing like progenitor mass, white dwarf mass. I'm just curious, like, what are some of the youngest white dwarfs?
I don't. I know that they are present in a 40 million year population. There are a sizable number of them. Alpha Per is the one that I'm thinking in particular. You might have a handful of them at ages earlier than that, but I don't remember it by heart.
Other questions? Yes.
Could you go through your last histogram with the fast and the slow rotators? So you might have mentioned this, but quickly rotating stars tend to be more magnetic magnetically active and then would have larger radii as a consequence. Do you expect this to bias your results as far as predicting SINIs?
If they are inflated, we should be able to still recover that through SED fitting. So when we are doing this bit right over here, we should still be able to measure their actual radii. So to some degree, maybe, because then the fluxes, the kind of how flux to the temperature might map would not necessarily be precisely the same, but we still should have, it wouldn't be quite as clear of a discrepancy as we end up having here. But yeah, this kind of affects all of the pre-main sequence stars equally. They all tend to be slightly inflated over there compared to the models.
A question from Doug? Yes?
I enjoyed seeing the picture of Orion and the runaway stars from Orion. Can you say anything about the mass distribution of those stars?
Oh, I think they tend, they come in all different masses. So there's a very famous pair of stars, AE, Aurigae, and Mu Col, that there are two OB stars that have been ejected, 2 million years ago? But there's also plenty of low mass stars that have been ejected as well. And I think right now the census of them is several dozen, probably closer to 60. I mean, this is a very massive cluster containing thousands and thousands of stars. So we just have a wide variety of things. And in fact, it's actually should probably be even more than that, because there is this long-standing question about, well, is Orion Nebula rotating with a virial velocity, or is it super virial, or what? Because if it's super virial, does it mean that it's not gravitationally bound or not? But what is most likely the case is that if you were to separate out the stars that are falling into the cloud, or into the cluster center, versus the stars that are falling out of the cluster center, the stars that are falling out tend to have a much larger velocity dispersion. So chances are there's a lot of binary stars that are in there, and many of these binaries would have been disrupted. And as they are moving on these fairly small velocities, so just 1 or 2 kilometers per second, nothing too crazy, so you wouldn't necessarily be able to separate them out. But just as a bulk of it, they tend to inflate the velocity dispersion of the cluster. Yes?
I have a question about early on when you were talking about star formation and you had the ring. You were talking about the history of formation there. Are there any thoughts as to what kind of event could cause a formation structure like that? And if you look at the radial velocity in that ring, are they all going away from us?
So regarding what event it could be, I mean, the supernova alone is probably not going to be sufficient. In Orion, you do have a lot of expansion. You do have these bubbles that have been formed as a result of supernovae, and everything is expanding there. For the local bubble, it's probably you need to have something a bit more energetic. I don't know what this could be. In terms of radial velocities, so in order to get radial velocities, you need to point at every single star with a spectrograph. And until recently, the places where we have been primarily studying things are much. So we have velocities here, here, and here. And as far as we can tell, these sightlines are expanding. We have no idea about the rest of it yet. But in the next couple of years with Sloan Digital Sky Survey, as we are able to map the galactic plane much more, we're hoping to be able to see it.
Very cool.
Yes.
You mentioned a factor of 10 for the future, and the number of stars we get ages for, and I guess it slipped by me. What's the data set that's going to get us there? Is it more Gaia data, more TESS data, more data?
Yeah, this is just with TESS, roughly estimating, well, how many rotating variables up to the period of 10 days there are in the Kepler data set. So how many bright stars there are in TESS, for which we would be able to measure rotational periods in general, and what would be the total number of stars if we had to apply the same fraction.
TESS doesn't go that faint.
16th magnitude, it's still a fairly sizable number.
So the idea is to get...
Yeah, so if we were to go from 1 million to 10 million, it's still not going to be every single star in the sky, but it's going to be a substantial improvement.
Any more questions?
I had a question. So a lot of cluster analysis is based off of the idea that all stars are formed at the same time.
Mm-hmm.
So I'm wondering, for a cluster, what is the intrinsic age scatter? And does this get larger for these loosely associated groups?
Yeah.
Pose any problems for this analysis?
I mean, so within a given cluster, you can have an age spread for a few million years. After you get towards the ages old enough, you're not really going to even see it. In Orion Nebula, it's the place where we have the largest age spread. I think it's on the order of 5 million years, but it's not necessarily all collocated. You can actually see the progression of ages as you go deeper and deeper down, and as you go deeper and deeper down, you have a more pronounced cluster. Throughout the entire cloud, you can have an age spread of around 20 million years. Again, still by the time that you reach a giga-year, it's not going to matter. Initially, that age spread does contribute to some scatter.
What about for these moving groups?
Oh yeah, I treat them simultaneously because these moving groups would form from a given Merkle cloud. These clouds can have the size of around 100 parsecs. So whenever you form a moving group, it will resemble the morphology of a cloud, which would collapse over a course of around 20 million years. At an upper limit. Sometimes it's usually less than that.
So we always say that in our classes, intro astronomy, that all stars are formed in clusters. Are we wrong? Are stars really formed in moving groups, not in clusters?
It depends on what you mean by cluster. And if you can give me a definition of what a cluster is.
Gravitationally bound. So the answer might be no, in a group, but not bound.
Yeah. So the thing is, when that statement was made in a rather famous review paper from 2003. They defined the cluster in a very specific way. And that term basically included all of the cluster populations, especially on the younger end, that have been known of at the time. So this statement wasn't really even true in how it's understood colloquially even back then.
So stars form in groups, but most groups dissolve, and a few of them remain as quote-unquote clusters.
Yes. So the stars form in clustered environments is what is a better term for that.
Cool.
What's the oldest moving group that you found in your set?
Over a giga-year. I don't remember the precise age. There's just only a handful of them. There's a handful of open clusters that have been known of that are older than that. But again, it's just a handful of them.
Just curious, just because the old gyrochromes are hard to get.
Yeah, all gyrochromes are hard to get with TESS. You can do it much more easily with other instruments. And maybe in future with LSST, that could certainly help filling up the older end much better than what we can right now with TESS.
Anything else? Last chance? This was fantastic. Thank you so much.